Welcome to the Deep Dive. Our mission, as always, is pretty simple. We take a dense stack of sources, articles, research, sometimes even forgotten history, and we try to pull out the critical knowledge you need to be, well, truly well-informed.
And today we're doing something a little different. It's not so much a technical dive as it is a professional one.
A philosophical one almost.
Yeah, exactly. We're looking at how the very idea of being a programmer has fundamentally changed. It used to be this image of the lone genius,
Yeah.
singular, isolated technical brilliance.
A wizard in the basement.
Right. And now it is absolutely defined by mandatory collaboration, by a deep understanding of the business you're working for. And that shift really is the hinge that modern software development turns on.
That transition from the lone wolf, the hacker, building what our sources call miracles in a basement, to this, modern team-oriented software professional, it's just loaded with friction.
Oh, it is.
And the sources we have today are fantastic for this. They're drawing really heavily on these unique personal recollections. War stories, really, from the 70s and 80s.
Which were the proving grounds, right? That's when all these ideas about what professionalism in code actually meant were being forged in the fire.
So what's the core tension here that you see across all this material?
I think it's this. Programmers, by temperament, often find comfort, a refuge in the clean, highly predictable world of machines.
The logic is pure.
The logic is pure. The results are deterministic. You put something in, you know what you're getting out. But professional life, it forces them to confront the two things they often try to avoid.
Which are?
Messy, unpredictable human beings, and the equally messy, complex, and, constantly evolving objectives of a business.
Okay, so our mission today is to unpack these specific stories. We're going to start with some early technical feats, some pretty serious optimization struggles.
And then we'll get into the deep psychological conflict of that programmer mindset. We'll analyze a really painful, career-defining personal failure. This firing anecdote is it's incredible.
Yeah, it really is. And then finally, we'll look at how dysfunctional team dynamics, specifically this destructive idea of owned code, defined and often just completely paralyzed engineering teams in the early days.
And the goal here is to give you those pivotal aha moments, the moments that show why just being good at code is only ever half the equation.
Like the realization that optimizing your code wasn't just a nice to have, it was intensely non-intuitive and demanded people working together.
And the shocking discovery that being the best coder on the team wasn't enough to keep your job. These are the lessons we really need to carry forward.
All right, let's unpack this. We're going to begin in an era that feels, it feels almost prehistoric to today's developers. The early days of hardware integration and this constant struggle for performance. So let's open the curtains on this story. We're in the mid-1970s, and our sources call this the DIY era. And that's not an exaggeration, is it?
Not at all. This wasn't just about writing software. It was intimate, hands-on engineering. The picture it paints is it's really beautiful. You have these two high school buddies, one of them Tim Conrad, building what they call miracles together in a basement laboratory.
And we're not talking about just assembling a PC from off-the-shelf parts.
Oh, no. This is a world of integration, not just abstraction. They were teaching each other how to program PDP-8s, these iconic 12-bit mini-computers.
Which were not user-friendly machines.
Not in the slightest. And they weren't just using pre-built components. They were physically wiring integrated circuits. They were soldering transistors, designing these rudimentary circuits from scratch just to get, calculator functions to work.
Wow. So it's this true synthesis of hardware and software happening at a very personal, very deep technical level.
Exactly. And their work, it pretty quickly moved beyond just hobby projects. They got into some really high-stakes industrial automation.
Right. The sources talk about systems that use lasers to trim electronic components, resistors, capacitors, for extreme accuracy.
And there's one example that just perfectly grounds this abstract world of code in, real consumer history.
What's that?
They were responsible for trimming the quartz crystal for the very first digital wristwatch.
Get out. The Motorola Pulsar.
The Motorola Pulsar. Think about that for a second. The physical timing mechanism that would basically define the entire consumer digital revolution was being fine-tuned by custom-programmed equipment that these two young programmers designed and debugged.
The margin for error must have been, microscopic.
Incredibly small. It demanded just extreme precision in their custom software. So you had these guys doing cutting-edge work, but on what we would consider incredibly primitive equipment.
So let's talk about that environment.
Yeah.
What was the specific machine, and how did its limitations really force this need for collaboration that we're talking about?
Well, the environment dictated everything. The computer was an M365, which was a clone of Teradyne's PDP-8.
Okay, so a mini computer.
A severely constrained mini computer. They were writing everything entirely in assembly language.
No high-level abstractions, no Python or JavaScript.
Nothing. And their source files, their actual code, was kept on these little magnetic tape cartridges. So the development cycle wasn't, type, save, run. It was, in the words of the source, quite involved.
I can only imagine. So if you can't just open a file on a screen, how do they even read and edit their own code?
With paper, massive printed listings.
You're kidding?
Not at all. Reading and doing your preliminary edits, that was all done on giant paper printouts because screen editing on those old terminals was incredibly cumbersome and limited. You'd literally take a red pen, mark up the paper, then go back to the terminal and try to punch in your changes.
That sounds agonizingly slow.
It was a slow, methodical, physically taxing process. And this right here leads us to the critical roadblock. The thing that slowed development to a crawl and sparked their first great collaborative effort.
Which was?
The core problem was code navigation. They had absolutely no facility for searching the code base.
So, no
Phew.
Ctrl plus F, no grep.
grep didn't exist for them. Today, you hit a key command and you instantly know every single reference to a variable, a function, a constant across your entire project.
Right.
For them, if you needed to know every place a function was called, you either had to rely on your own memory,
Which is a terrible idea.
a terrible idea, or you had to physically read through miles of that printed paper hoping you didn't miss one. This lack of visibility made any serious debugging or, feature development a massive, intimidating hindrance.
Okay, so the pain is real. The solution they came up with, it wasn't for fun. It was out of pure, desperate necessity.
Exactly. They decided to write their own utility, a cross-reference generator.
What would that do?
Its function was simple, in theory. It would read all the source tapes, parse the assembler syntax, and then generate a new listing that showed every symbol used in the code, along with the specific file and line numbers where it was referenced.
A modern-day IDE does that in the background without you even thinking about it.
Right. And their initial method was pretty straightforward. Read the tape, parse it, build a symbol table in memory, and then just add the references as you find them.
And this is where we get to that classic story of optimization failure. The program worked, technically.
It worked, but its performance was catastrophic. They tried to process their main piece of software, which they called the MOP, the Master Operating Program.
The MOP.
And they loved that. And the program was, quote, horribly slow. We are not talking about a few seconds of lag here. We are talking about a processing time that stretched out to over an hour.
An hour. To process one program.
For a single run. Now think about that. If your core development tool, the thing you need to understand your own code, takes an hour to run every time you make a change, you've basically just halted all professional productivity.
It's completely unusable. You'd never run it.
Yeah.
So what was the technical blunder? What was the fundamental mistake that caused this?
It was a pure knowledge gap. And the source is very humble about this. They were self-taught in this environment, and they admitted they were not experts in computer science fundamentals. They had, and this is a direct quote, never heard of hash tables or binary searches.
Wow. Things that are, CS 101 today.
Absolutely. They just didn't have that theoretical framework for efficient data storage and retrieval. It wasn't common knowledge outside of academia yet.
So without those essential tools,
Yeah.
what were they doing? How did they manage this growing symbol table in memory?
Okay, so they held the entire thing in one single contiguous memory buffer.
Like a giant array.
Exactly. And every time they found a new symbol or a new reference to an existing one, they had to insert it into that table. And they wanted the final output to be sorted alphabetically, so they had to insert it in the right place.
And this is where the memory constraint and their simple algorithm just collide.
It's a nightmare scenario. Imagine this physical process. You have this massive block of memory, and it's holding thousands of symbol entries, all sorted. Now you find a new reference that needs to be inserted right in the middle.
You can't just stick it in.
You can't. You have to physically shift every single subsequent entry down a few bytes to make room.
Oh, that's brutal.
And as the table grew, this process got exponentially worse. The time it took for each insertion was directly proportional to the size of the table, which leads you to that paralyzing quadratic scaling. The more information they added, the slower and slower the tool became until it was useless.
And this is the moment. This is where the professional value of collaboration is really born. They realize they can't solve this alone.
They couldn't. And they couldn't just walk away from it because the tool was absolutely mandatory for professionalizing their own development process. They needed it.
So what did they do?
The source recalls that they collaborated like fiends. And I love that phrase. They weren't just, sitting at separate terminals typing. They spent hours standing together at a whiteboard, drawing diagrams, visualizing memory structures.
Trying to invent data structures on the fly.
Literally. They were performing manual calculations, trying to predict how many machine cycles a new approach might save. They were inventing solutions in real time, often without knowing the formal names for what they were trying to build.
And the attempts they made at first, they sound like just brilliant desperation, a series of what they called crazy ideas.
They were trying to outsmart the system without the formal training. They experimented with methods like leaving intentional physical gaps in the memory arrays.
What was the theory there?
The hope was that future instructions would just happen to fall into one of the gaps, which would minimize the amount of shifting they had to do.
And when a gap filled up,
They'd have to restructure the whole thing. They even tried building these complicated linked lists on top of the gaps. It was this high-intensity, iterative, probably maddening period where some of their attempts actually made the program even slower than the original hour-long run.
but eventually, this synthesis of their two minds, it paid off. The breakthrough came.
It did. They cracked it. They managed to get the processing time down to under 15 minutes.
From over an hour to under 15 minutes, that's a huge win.
It's a massive win. But here's the critical insight. Why were they so satisfied with 15 minutes? That still sounds pretty slow today.
Because that was the physical limit.
Exactly. It was nearly the time it took just to physically read the entire source code off the magnetic tape itself.
So they had optimized the computational part of the problem so much that they were now bottlenecked entirely by the hardware, the I/O speed of the tape drive.
Precisely. They had achieved the theoretical optimum for that specific hardware setup. And the lesson wasn't just, hey, we fixed the code. The lesson was profoundly professional. It was that optimization is incredibly difficult. It often defies your intuition.
And you can't do it alone.
You can't. It requires that shared mental energy, that collaborative friction of multiple people working fiercely together, combining different ways of seeing the problem to reach that maximal efficiency under these severe constraints. And that, for them, was the birth of true professional partnership. So they mastered how to collaborate to serve the machine. But now we move to the next, and often a far more challenging hurdle: collaboration in the service of people, in the service of the business.
Right, and this brings us head on into what the sources call the core mindset conflict that defined, and frankly still defines, a lot of programmers.
It's the identity, right? The identity is central to this. Programmers fundamentally are often drawn to the field because they have a preference for logic over emotion.
It's a deep-seated preference.
Very deep-seated. They didn't become programmers to work with people. I mean, they find interpersonal relationships with their endless variables and contradictions and politics to be
Messy and unpredictable.
That's the perfect phrase. Their clear preference is for the clean and predictable behavior of the machines they program. The computer is a reliable, if sometimes frustrating, partner. People are not.
And that sounds like a really powerful psychological pull. What does the ideal working environment look like for someone with that mindset?
The ideal scenario is deep, singular focus. It's being alone for hours, deeply immersed in an interesting technical problem. The sources talk about this as an enjoyment of mild sensory deprivation.
The cocoon-like immersion of focus.
Exactly. That state where the external world just kind of fades away and only the problem remains. That's often where a programmer feels most productive and, honestly, most comfortable.
And we should say, this is a generalization, right? Not every coder is an isolated hermit.
Of course, there are exceptions, but it reflects the group average tendency. It's the gravitational pull of the field. And this is where the requirements of being a professional slam directly into that comfort zone.
And this is the moment of conflict.
It is, because professional responsibility dictates that your success isn't measured in lines of perfect code written. It's measured in value delivered to the organization. The mandate extends drastically beyond the elegance of the code itself.
So what, according to these sources, is the defining worst transgression a professional programmer can commit in this context?
The worst transgression is when a programmer blissfully buries himself in a tomb of technology.
The ultimate cocoon.
Yes. While the operational, financial, or political needs of the business are just collapsing around him, that isolated genius who delivers perfect code 3 months too late, or code that solves a problem the business no longer even cares about. That person is a professional failure.
So the first responsibility isn't to the code. It's to the employer's needs, which means the programmer has to, you know, step out of the cocoon and engage directly with those messy human elements.
Exactly. You have to become, at least partially, a business wonk. You have to collaborate deeply with managers, with business analysts, with QA testers, and most importantly, with your fellow team members to actually understand the core business goals.
You can't just read the spec and start coding.
No. If you're automating a factory, you have to understand production quotas and the cost of downtime. If you're building a banking app, you need to understand regulatory compliance and customer retention goals.
It's the so what factor. It's not just how you write the code, but truly understanding why you are writing it.
And how it provides a tangible benefit. If you miss that connection, if you create a technically brilliant solution that costs twice what the business can afford or solves a low-priority problem while a high-priority one is on fire, you have failed your professional duty. It doesn't matter how good your code is.
So how does a professional programmer actually do this? How do they operationalize this external engagement and bridge that gap?
They have to dedicate time and energy to those unpredictable people. They have to go talk to users to understand the real-world usage patterns, the pain points, the workflows, not just what the specification said, but what the reality is.
And it goes beyond just the users.
Oh, yeah. They talk to sales and marketing to understand customer issues and market demands. And they talk consistently to their managers to understand the shifting short-term priorities and the long-term strategic goals.
It's all about situational awareness.
It is entirely about knowing, as the source puts it, which ship they are sailing on. If the company is pivoting to a new market, your programming goals have to pivot first. If the company is facing an existential crisis because of some regulatory failure, your focus has to shift immediately to compliance. That external awareness is completely non-negotiable for a professional.
This inherent conflict between that deep technical focus and the professional context, it leads us directly to the most critical and painful story in our source material.
The firing anecdote.
Yeah. This story just lays bare the real-world consequences of that kind of isolation.
This is the emotional anchor of the entire professional argument. It takes place in 1976. The narrator is a young programmer, just 24 years old, and he's working at Outboard Marine Corps.
What's the job?
He's writing a complex factory automation system. They're using these IBM System 7 mini computers to monitor aluminum die-cast machines on the factory floor.
So from a purely technical perspective, this sounds great. This is exactly the kind of challenging, engaging work that a programmer would crave.
Absolutely. He describes it as challenging and rewarding. The architecture of the IBM System 7 was fascinating to him. The automation system itself was really interesting. He had a good team, a competent manager named Ralph, a pleasant team lead named John. They worked enthusiastically in their own dedicated lab.
So everything, technically and socially, within that team bubble was set up for success.
It was. But the narrator, at 24, he carried that fatal flaw we just discussed. This arrogance about the importance of technology over people and politics.
He was deep in the cocoon.
Deep in the cocoon. He admits he simply could not bring myself to care about the business or about its internal political structure. He believed his job was to solve the technical problem elegantly, and everything else was just a trivial distraction.
And this flaw, it showed up almost immediately in a small but incredibly significant detail.
The tie.
The tie incident.
On his first day, he shows up, and he's not wearing a tie, even though he notices everyone else, including his manager, Ralph, is formally dressed. Ralph has to pull him aside and just state the expectation plainly. We wear ties here.
And this wasn't just, like, a simple fashion mistake. It was an active rejection of the professional convention.
It was. And his response wasn't just simple compliance. It was this deep internalized resentment. That's the key psychological detail.
And he wore the tie.
He wore the tie every day after that, but he hated every single minute of it. He hated the convention because he fundamentally believed that arbitrary human rules shouldn't apply to him, the brilliant engineer.
That's a dangerous mindset.
And it leads him to this brutal self-assessment later in life. He realized he was acting like a selfish, narcissistic little twerp. This little detail about the tie, it just shows you how deep that emotional barrier was between his technical world and the corporate one.
And despite this attitude, his technical self-assessment was incredibly high. He really believed he was doing a great job.
He genuinely did. He felt he was the best technical programmer on the team. He was writing faster, more efficient code, diagnosing problems quicker than anyone else. He was quantifying his success purely by technical metrics.
And he was prioritizing that technical elegance above everything else.
Everything. Deadlines, formality, times, dates. He believed they simply weren't important compared to the pure quality of his technical solution.
And this internal clash between his values and the company's values, it leads directly to the critical moment.
The milestone demonstration. The team lead, John, had communicated that a high-stakes demo was scheduled for Monday morning. Now, the key context here is that the system was still under active development. It wasn't in production yet.
Okay.
The programmer, believing his technical focus was paramount, he didn't prioritize this demo. His reasoning was, well, since the system isn't in production, there's no reason for it to be running over the weekend.
So he left the lab on Friday afternoon, and he left the IBM System 7 in a non-functioning state.
Correct. The importance of this Monday demo, it did not register in his insulated worldview. He was already focused on his next technical challenge, not the team's professional presentation.
And then comes the inevitable Monday morning.
He arrives late, of course, which is consistent with his whole attitude, and he finds the entire team gathered glumly around this cold, non-functioning system.
And he's clueless at first.
Totally clueless. He sees the distress, but he can't connect it to his decision on Friday. He just starts debugging, still viewing it purely as a technical problem to be solved.
And then the moment of realization comes from his team lead.
John walks over, and he is just completely disgusted, and he whispers the line that changed this programmer's understanding of professionalism forever.
What did he say?
He just looked at him and said, "What if Stenberg had decided to visit?"
And Stenberg was?
The vice president in charge of automation. The modern equivalent would be the chief information officer, the CIO.
So for the isolated programmer, the response is probably, so what? The system isn't live. But why did Stenberg's potential visit matter so profoundly to John and to Ralph?
Because it had nothing to do with the code's live status. It was about professional commitment and the political structure of the company. When an executive who is responsible for these massive automation investments makes a surprise visit, they expect to see their investment running. They expect to see progress.
And the programmer's failure meant the whole team looked bad.
It meant the entire team, and John and Ralph specifically, looked incompetent and unreliable. It erodes political capital. It erodes trust. It was a massive professional failure.
So he gets his first warning letter later that day.
Yes, stating that any further issues would result in quick termination. And that was the seismic shock to his technical ego.
It must have been horrifying.
It was. It finally shocked him out of that narcissistic cocoon. He was forced to analyze his own behavior, and he started to realize the extent of his professional negligence. He tried to pivot. He started paying attention to the internal politics, genuinely trying to understand John's anxiety and why Stenberg's random presence mattered so much.
He realized too late he'd been undermining his own team.
Exactly. He tried to redeem himself, but the momentum was already against him. It was too little, too late. About a month later, he got a second warning letter for what he perceived as a trivial technical error.
And at that point, he knew.
He understood the decision had already been made. The paperwork was just a formality. His fate was sealed not by technical incompetence, but by his professional negligence.
And the story ends with a termination meeting and him walking home at 24 years old with a pregnant wife waiting for him.
The pain of being fired was immense, but the lesson was just as powerful. He learned the hard truth. Technical brilliance does not give you a pass to ignore the business, the team, or the professional standards of the organization. The job of a professional is to serve the business goal, and that requires managing people, expectations, and politics, often more skillfully than you manage the code itself.
That moment was the necessary, brutal transition from being a gifted amateur to becoming a true professional engineer. Okay, so the programmer must collaborate with business. That lesson was learned the hard way. Now, let's pivot to the friction within the technical team itself. The difficulty programmers often face when working closely with other programmers.
And this dynamic failure often leads to what the sources call terrible problems.
This is the internal version of that same isolation, and it's just as destructive.
It is. And the central symptom of a dysfunctional engineering team is this concept of owned code.
Owned code. That sounds highly toxic. How does it actually manifest, and why is it a recipe for disaster?
Owned code is when each individual programmer effectively builds a defensive wall around his code. They treat their module, their function, their part of the system as their own personal property.
My code. Don't touch.
Exactly. They actively refuse to let other team members review it, debug it, or make changes to it. They become the single point of failure and the sole gatekeeper for that entire knowledge domain.
And the sources give us a powerful, specific industry example of how this crippling dynamic played out within a company that was building complex machinery.
Yeah, the high-end printer company example is perfect because it shows how the business structure itself can inadvertently encourage this kind of technical isolation.
So what was the setup?
The company built these very complex printers that had multiple distinct mechanical and software components. You had sheet feeders, the printer engine itself, stackers, cutters, staplers, and so on.
And crucially, the business didn't value all these devices equally, right?
Not at all. The company understood that certain parts were more critical to the core operation than others. For instance, the feeder mechanism might have been the most complex, the most error-prone, or the most vital component in the whole device. The stapler, maybe, was secondary.
So how did the programming team organize itself around that business reality?
They organized by device, but with a competitive, territorial twist. Each programmer maintained the code exclusively for his device. The person who wrote the feeder code worked only on the feeder. The person who wrote the stapler code worked only on the stapler.
And they guarded that knowledge.
They cultivated expertise, and then they guarded it, actively preventing any other team member from touching their repository.
So this technical isolation was directly linked to the hierarchy of the business components they were supporting. How did that create a political and financial disaster?
Well, this is the really insidious part. The programmers' political clout, their leverage inside the company, and most critically, their salary reviews were directly related to how indispensable they were.
Which was related to the business value of the device they controlled.
Precisely. If the feeder broke, the entire production line stopped, and only the feeder guy knew how to fix it. This made his position, in the words of the source, unassailable.
So they had a powerful, direct financial incentive to maintain these crippling knowledge silos and prevent anyone else from learning their code.
They were paid, essentially, to be a single point of failure. Why would the feeder programmer teach anyone else his proprietary knowledge when his salary review literally depended on his absolute unchallenged ownership of that critical piece of code? The moment he taught someone else, his leverage diminished.
So what was the inevitable technical cost of this arrangement? What did the overall software architecture look like?
An unmaintainable mess. The costs included massive, unnecessary code duplication because programmers couldn't share libraries or common functions without crossing these invisible ownership boundaries.
And the interfaces between modules must have been a nightmare.
Skewed, highly inefficient interfaces because they were designed defensively, based on individual pride and protecting territory, not on unified architectural requirements. And any efforts by consultants to reform the organization failed repeatedly because the programmer's self-interest was economically protected by the status quo.
So the professional solution here has to be a hard pivot to collective ownership. You have to actively dismantle those internal structures that reward isolation.
Collective ownership is the only antidote to owned code. The philosophy has to be ingrained from the top down. The entire team owns all the code, all the time. The goal is that the unit is responsible, not the individual who happened to check in the code originally.
And what are the practical benefits of that model? How does it fundamentally change the team dynamic?
Resilience and transparency. Any team member has to be able to check out any module and make necessary changes. Professional developers, they actively break down those walls of ownership. They're expected to work with each other, to learn from one another on all parts of the system.
So if the feeder code needs a fix at 3 a.m., and the original author is on vacation,
any other team member has to have the familiarity and the authorization to jump in and solve the problem. It distributes knowledge, and it eliminates those single points of failure. It makes the whole team stronger. So once you accept the necessity of collective ownership, you need a mechanism to actually enforce it. And the most efficient, active mechanism for mandatory collaboration that our sources highlight is pairing, pair programming.
and this is where we run right into that central conflict again, isn't it? Many programmers, they dislike pair programming. It violates that deeply held desire for the cocoon-like immersion.
It's the great irony of the profession. Programmers often view pairing as inefficient or distracting or just annoying, yet professional experience proves the old adage, 2 heads are better than 1.
How so?
When you have 2 minds intensely focused on a single piece of code, errors get caught faster. Design flaws are spotted earlier. The implementation just becomes more robust because you're constantly questioning each other's assumptions.
And can we talk about why it's so critical in high-pressure situations?
Absolutely. Speed in emergencies. When you have a production-level crisis, a SEV1 bug, the quickest way to find and fix it is not to have one person frantically searching alone. It's to have two people working collaboratively, trading the keyboard, challenging assumptions, and cross-checking each other's knowledge.
So professionals pair because they prioritize the efficiency of the solution over their personal preference for quiet focus.
Exactly. It's about what's best for the business and the product, not what feels most comfortable for the individual.
And beyond that raw problem-solving speed, pairing is also instrumental in solving that knowledge silo problem we just talked about in the own code section.
That's its secondary but equally vital function. Professionals use pairing as a preventative measure. It's not just for emergencies. By mandating regular rotation of pairing partners and tasks, team members naturally learn different parts of the system.
And crucially, they learn the nuanced business logic that's applied to those different components.
Right. It becomes this continuous real-time cross-training mechanism. It ensures what the sources call team readiness.
Meaning that even if everyone has a specialty, their primary position.
Everyone can play another position in a pinch. If the owner of that business-critical module leaves the company or goes on vacation, there are three other people who have recently worked on that code and understand the core architectural decisions. That resilience is just invaluable to the business.
And the sources also highlight pairing as the gold standard for code review. They say it effectively eliminates other, slower methods.
Yeah, they're pretty unequivocal here. Any system striving for professional quality should consist only of code that has been reviewed by at least one other programmer. And traditional asynchronous code reviews, reading diffs in isolation, formal review meetings, emailing code snippets back and forth, they're deemed horrifically inefficient. Because the feedback loop is too long, the context is lost. Pairing is the most efficient and effective way to collaborate in writing code because the review is instantaneous, it's continuous. It prevents errors from ever even being checked in the first place.
This systematic commitment to visibility and collaboration, it's such a fundamental shift. And it even allows us to critique a famous public attempt to celebrate this very concept.
Ah, yes, the cerebellum's metaphor.
This anecdote is just a perfect snapshot of the dot-com era's struggle to understand collaboration, isn't it?
It really is. It happened in Chicago around the year 2000. There was a massive recruiting billboard for a software firm, and it read, "Come rub cerebellums with the best."
And their intention was good, right? They were trying to project this image of intense intellectual exchange and knowledge sharing.
The intention was good, but the execution exposed a profound disconnect with their target audience.
They demonstrated what the source calls rank stupidity.
I mean, think about it. You're trying to attract a highly technical, educated audience of engineers, yet you get your basic brain anatomy fundamentally wrong.
So what's it the cerebellum actually do?
The cerebellum, which is at the rear base of the skull, it controls fine motor movements, posture, balance, coordination. It has nothing to do with intelligence, abstract thinking, or the kind of high-level knowledge exchange they were trying to convey. That's the cerebrum.
So the ad failed on a physiological level, but also on a metaphorical one.
Absolutely. The physiological error was just embarrassing to a scientifically literate audience. But the metaphorical failure, that's the deeper lesson about collaboration. If a group of people tried to physically rub that part of their brain together,
And have to turn away from each other.
they would literally have to face their backs to the problem and to each other. It's the visual antithesis of professional collaboration.
Which drives us to the final definition here. If collaboration is not rubbing the backs of your heads together, what are the necessary physical and psychological conditions for professionals to work together effectively? What is the true opposite of that programmer isolation?
The opposite of isolation is mandatory sensory connection. Professional work demands that professionals work together, physically. They cannot sit at separate screens wearing noise-canceling headphones, lost in their own little worlds. The environment has to facilitate that connection.
The physical layout itself has to prioritize communication.
Yes, it means sitting around tables or desks arranged so that people are facing each other, not facing walls or monitors. It means being close enough to overhear what the source calls serendipitous communication.
What does that mean?
It's the verbal exchanges, but also the critical body language. You need to be able to hear a frustrated mutter from across the table or see a sudden slump of the shoulders that tells you someone is blocked. The source uses this incredibly vivid phrase. You need to be able to smell each other's fear. It describes the level of sensory immersion that's required to function as a unified problem-solving unit.
So while we acknowledge that deep focus is sometimes necessary, the professional reality is that most complex work benefits from that constant, immediate feedback.
That's the balance you have to strike. There are certainly times when deep individual thought is required and silence is necessary, but it is highly unlikely that you work better alone and in collaboration for any large, complex, non-trivial task. The professional mandate is clear. For a large fraction of your time, you have to collaborate closely, actively sharing knowledge, and resisting that gravitational pull back into the comfortable cocoon of isolation. Hashtag tag tag outro. So as we synthesize this whole historical journey from, the hours they spent optimizing the MOP through the brutal lesson of the firing at outboard Marine and the architectural decay caused by owned code, the core lesson for the professional programmer, it remains difficult, but it's unavoidable.
The programming paradox. You have to embrace it.
You must. Programmers may have been drawn to the field, seeking refuge from the unpredictability of people, favoring the clean logic of the machine. But tough luck.
Yeah.
Programming as a professional enterprise is all about working with people. You must work with the business, understanding its goals and its politics, and you absolutely must work with each other, sharing ownership and collaborating intensely.
The fantasy environment that we talked about versus the reality is a perfect final contrast here.
The fantasy is so seductive, isn't it? The isolated, perfectly configured workstation. You've got 6 massive screens, a T3 pipe, super fast processors, unlimited memory, and an endless supply of high-end snacks and Diet Coke.
That's the realm of the individual genius.
It is, but the reality is, if you want to be effective and stay employed professionally, you are going to spend a substantial part of your day in meetings, at whiteboards, or sitting side by side with a colleague. You are going to learn to talk to people.
And that essential connection brings us back to you, the learner. The key takeaway from this whole historical evolution is that the path to professionalism isn't just about incrementally faster code or more complex algorithms.
Technical mastery is mandatory, it's the table stakes. But it's only half the job. True mastery lies in synthesizing that elegant technical solution with the business's human, often chaotic, goals, and maintaining the discipline of collective code ownership.
And this leads us to a final, provocative thought for you to carry forward, something to mull over.
If we accept that collaboration, communication, and business acumen are not soft skills, but are actually technical requirements,
As necessary as knowing how to implement a hash table or a binary search.
how drastically does that shift the way we structure our teams, the way we evaluate success, and the way we hire engineers today? Does collaboration need to be tested as rigorously as algorithmic knowledge?
A question that could fundamentally redefine the scope of computer science education. Something to chew on long after this deep dive is complete. Thank you for joining us. We'll see you next time.